Well, thank you all for coming. If I say anything incoherent or stupid, you know why. God makes sense. But it's a great pleasure to have Eve Lee speaking with us today. I've known Eve for over a decade, and actually, when I first met her, she did me an enormous favor because she was an undergraduate in a class I was TAing at the University of Toronto. And after I got the first homework set, I realized that I didn't need to prepare any solutions because Eve always did everything perfect. And so all I would do is I'd look at Eve's solutions and be like, oh, that's how you do that problem. And then I could go and grade everybody else's. And I remember several times in office hours, her asking me a question, and I was like, oh, I'm totally screwed here because she knows more than I do. So she has gone on to be as impressive as one could ever imagine. So she, after finishing her undergraduate degree at the University of Toronto, she stayed there for a master's degree and then moved to Berkeley to do her PhD with Eugene Chang, where she began really challenging a lot of the basic conventions about what we think we know about planet formation, and she's continued to do groundbreaking work on a wide range of sort of close-in planets. She's coined some cool terms like super puffs. I think I can give her credit for that one. And then she moved on to a postdoctoral position, the Sherman Fairchild Fellowship at Caltech, and she is scheduled to start her faculty job at McGill in the fall, where she will freeze her off, I'm sure. But she's from Toronto, so she's prepared. So she's going to tell us about all the different types of cool planets she's worked on. So take it away.
Thank you so much for the very kind introduction, Caitlin. I'm glad to hear that I saved your time as a TA back in the days. So let's talk about exoplanets. One thing that excites me the most about exoplanets right now is their diversity. We have about 4,000 planetary candidates that we have detected, and that really tells us that there's a huge diversity in the planet radii, their masses, the properties of their orbits, as well as the properties of the stars that they orbit. And that we can use that information to say something about the different formation scenarios and what gives rise to their large diversity. And the key physical parameter that we can use is the planet occurrence rate. In particular, how that changes as a function of planet sizes as well as orbital periods, and you can also look at them as a function of the stellar spectral types, metallicity, and for this crowd, also the stellar multiplicity. So looking at this plot, one thing that really jumps out at me is that there's some sort of clear divide in the kind of planets where you have a different morphology in the orbital period distribution. So if you divide right at the size of the Neptune, which is about 4th radii, those that are smaller rise up to about 10 days and they plateau. But if you look at those larger planets, they just continue to go up. So what's so special about this divide? When it comes to the size of the planets, that's really driven by how much gas these planets have. So the Neptune-sized planets corresponds to gas to core mass ratio of about 10%. So this different morphology tells us that, perhaps it tells us that this gas-poor planets versus the gas-rich planets, they follow different formation scenarios. And looking more closely at this gas-rich planets, if you look at the sub-Saturn, so that's 4 to 8 Earth radii, compared to the gas giants, you'll see that they almost lie right on top of each other. And if you just integrate this up, they have about the same occurrence rate. So we find just as many sub-Saturns as gas giants. And that's actually really surprising, in particular in the context of the classical theory of core accretion, where the idea is that you have some solid core sitting in the gaseous nebula, and over time it's going to slowly accrete gas until the gas mass becomes comparable to the core mass, and you trigger this runaway gas accretion. The overall underlying physics is basically the thermodynamics of these envelopes. The rate at which you slowly accrete gas is governed by the cooling rate of the envelope. So this runaway gas accretion just corresponds to the fact that the self-gravity of the envelope becomes important, and it triggers the thermodynamic instability, where the cooling time scale just gets shorter and shorter as you accrete more and more. So just looking at this plot, naively, you would expect a very clear bimodal distribution of planets, those that are gas poor and the gas giants, and nothing in between. However, sub-Saturns fall right at this ascent of this runaway gas accretion. So it's mysterious. How is it that we find just as many sub-Saturns as the gas giants, because we really shouldn't have seen that many? The answer comes in two parts. The first part is that the time at which this runaway occurs, it's a very sensitive function of the core mass. It goes as about core mass to the negative 4.5 power, so it's very steep. But more importantly, the second part of the solution is that we have to stop this runaway at some point. This is a very, very strong signature and just really hard to hide that away. So how are we going to stop that? Let's look more closely at the different modes of gas accretion, starting from this thermodynamic accretion. So the very basic physical picture of the core accretion, as I said, is from cooling of the envelope. The picture is that you have some solid rock sitting in a gaseous nebula, and it's going to hold on to the gas within its hair radius or boundary radius, whichever is smaller. That envelope is going to cool and contract over time, which leaves some empty room for the ambient gas to refill. So in this mode, the time scale of accretion is set by the time scale of cooling. And if you want to look in more detail of what sets the rate of cooling, you have to know the structure of these envelopes. And in general, you start with the outer radiative layer and the inner convective zone. Mass is centrally concentrated, which means most of the energy is inside this convective zone. So that the bulk cooling timescale of this entire envelope is set by the cooling timescale of this inner convective layer. And whenever we talk about the rate of convective energy transport, it's the lid that limits how much energy can escape out of this convective zone. So it's this radiated convective boundary that controls the rate of cooling. So the way to think about that is energy tries to escape out of the convective zone into the radiative layer. Radiative energy transport is set by the local temperature gradient, which by definition is maximized at the radiative convective boundary. So that sets the absolute upper limit on how much energy can escape out of this convective zone. So we have to know the thermodynamic properties of this radiative convective boundary, and that depends on the opacities. So as long as you have some dust grains in the upper layer, which contribute to the overall opacity, the zone at which this boundary occurs is almost always at the hydrogen molecule dissociation front. Reason being that once you have the free hydrogen atoms, it can combine with the free electrons that came off of valence electrons from some metallic species. Then you can create H- ions. Then the bound-free transition of this H- ions become the most dominant source of opacity. And you have this surge of opacities on the inside because H- opacity is a very sensitive function of the temperature. So that ensures convection always prevails. And what that tells you is that a priori, you can get a sense of what is the thermodynamic properties at the radiative convective boundary. For example, the temperature of the H2 dissociation front is almost always at 2500 Kelvin. This allows us to write down analytically how the envelope mass grows with time as a function of the core mass. So starting parts can be written down and can be explained in like a couple of minutes, so I'll just go through that. In this mode, the accretion timescale is set by the cooling timescale, which is just internal energy divided by luminosity. To order unity, the internal energy is simply given by the gas mass sitting in the gravitational potential of the core. And the luminosity is given by the radiative diffusion at the radiative convective boundary, which of course scales with the photon mean free path, which means it's going to scale inversely with the density, so it's going to scale inversely with the gas mass. If you combine all of that, then you'll find that the gas mass grows as the square root with time. So it's a sublinear, pretty slow growth. And if you're more careful, you can derive the full scaling relationship between the envelope mass fraction, the time, atmospheric metallicity, and the core mass. Putting in all the right numbers, you'll find that the gas mass fraction grows as time to the 0.4 power, so close to 0.5. And it's a very sensitive function with the core mass growing as core mass to the 1.7th power. This plot is here just to demonstrate to you that there's a very good agreement between this purely analytic calculation, which is given in red dashed line, compared to the numerical calculation, which is given in the solid line. And just FYI, this numerical calculation was motivated by the work done by Andrew Yoden and his previous student, Anna Maria Pizzo, where we take the hydrostatic snapshots, which is simply a solution to the stellar structure equations, and just calculate the time it takes to go from one snapshot to the next to string them together to draw this time evolution of the envelope mass fraction. This growth of the envelope mass by the thermodynamics, in other words, by the cooling of the envelope, requires certain minimum mass of the core. At the very minimum, the core escape velocity has to be larger than the local gas sound speed. And it's the reason why we are not exactly accreting this atmospheric gas that we're all sitting in or sending in. In the inner regions that we're interested in, this corresponds to core masses of about twice that of the moon. Another thing to keep in mind is that for accretion by cooling, there's an absolute maximum mass of the gas that these cores can have, which is set by this isothermal atmosphere, which just means the entire envelope has been thermally relaxed to the nebula. And for, again, in this inner regions, if the core mass is smaller than about the Earth, then the maximum envelope mass is just so small that you would practically call them as bare rocky objects. So close in sub-Earth mass cores can only remain as rocky. Now, what about on the opposite end of the spectrum? And let's look at what happens to the massive cores, where these massive cores are the most subject to rapid gas accretion and therefore nucleating the gas giants. And I started this discussion by saying that we need some mechanism to stop the runaway gas accretion so that we see just as many subsaturns as the gas giants. Now what happens is that you can launch the runaway, but you cannot really prolong it because at some point the accretion is no longer be mediated by the thermodynamics but by hydrodynamics. In other words, the local gas delivery onto these planets. So in this limit, there have been a lot of studies, especially the numerical calculations, where they have reported some empirical fits to their numerical results, but for whatever reason, nobody has written down sort of analytic understanding of how to get their scaling relationships. But in certain limits, that's pretty easy to write down, so I'll just quickly go through that. Let's think of in the limit where the planet's heel radius is larger than the local disk scale height. And again, in this inner regions, you don't need that much mass to have this limit. You only need about 8 to about 10 Earth masses. So the mass accretion by hydrodynamic flows, at the basis, you can think of it as your classical bonding accretion, like the formation of the stars. The difference here is that the planet is not sitting in some infinite medium of gas. Rather, it's sitting in a disk of gas. So you have to worry about the geometry. So, but at the end of the day, the mass accretion is simply the accretion cross-section times the density of the inflow gas times the velocity of the inflow gas. The accretion cross-section, you can take it as sort of cylindrical cross-section, so 2 pi here radius times the local disk scale height. Now, what about the velocity? The velocity as the flow approaches this Hill radius, the relative velocity between the flow and the planet, there are two components, the gas down speed as well as the shear velocity at the heliosphere. But in this limit, the shear velocity is going to dominate, which means as the flow comes in, it's going to shock. It's going to lose energy and fall onto the planet. So you can take the velocity of the inflow gas, or rather the accretional flow, as the free fall velocity at the Hill radius, which actually to order unity is simply the Hill radius times the Keplerian frequency. Now what about the density of the inflow? So because it's a shocked material, you need to take the post-shock density, which in the strong shock limit is going to be the background density times the Mach number squared. So if you combine all of this, then the m dot, the gas accretion rate, goes as the planet mass to the 4/3 power, which means it's much slower than this sharp runaway gas accretion. And this is the exact scaling relationships that people have found by empirically fitting to their numerical results. Now looking at this, unlike the gas accretion by thermodynamics, the hydrodynamic flows does depend on the local disk gas density. And it's a bit unclear where to take this density. Should you take it like some farther way out, or perhaps you have to worry about the disk and planet interaction, because this planet, especially if it's this large, is going to perturb the disk. In particular, it might create some kind of gap. Classically, people have quoted the sort of like strong shock, that thermal mass limit, which just goes back to where Hill radius becomes larger than the local disk scale height, as the criterion for the gap formation. But in reality, if you the actual physics is not really that, but the forces, or rather the torques that you need to compare, is the one-sided tidal torque from the planet versus the viscous torque that's trying to erase all the perturbations that's being occurred in the disk. So if you just balance these two, you can write down what is the mass ratio between the planet and the star, so that you can create an appreciable amount of depletion within the local gas. Now, as you go to a lower and lower viscosity, it's going to be harder and harder for the disk to erase away its perturbation. So that means you don't need as much mass within the planet to carve out these gaps. So if you go to really low viscosity parameter, the alpha parameter of, let's say, 10 to negative 4 or lower, then you only need about like Neptune mass objects to carve out such gap. And by gap, I mean the density depletion of about order unity to an order of magnitude. So perhaps you need to take the density at the bottom of the gap when you calculate the hydrodynamic accretion flow onto these planets. So sort of a quick summary of what are these different modes of gas accretion onto the planets. First, we looked at the thermodynamics, so accretion by cooling. And then we looked at the local hydrodynamic flows. But there's a third mode of accretion, which comes from the global gas supply. So the upper two, they are all local effects, but it's possible that both of these are so fast that the global gas supply by the global viscous drift or viscous spreading cannot catch up to them. And in that case, it's going to be this global disk accretion that's going to limit how much gas these planets can hold on to. So with these three different modes of accretion, at any given time, how much gas these planets will accrete and hold on to is going to be determined by which of these three modes give you the lowest amount of accretion rate, because that's the limiting factor. So here's a comparison with the different color corresponding to different core masses. The solid line is for cooling. The solid gray line is the global disk accretion. You'll notice that there's a sharp cutoff right at around 1 million year. That corresponds to those 2 time scale disk depletion, where this is the global viscous accretion, and then the photo evaporation from the host star carves out a gap at around the wind launching radius, which which decouples the inner disk from the outer disk, and the inner disk just drains away much quickly. And that's the reason why there's a sharp cutoff right at around 1 million year. And then the local hydrodynamic flows are given in the dashed line. So just looking at this, depending on what kind of core masses you have, you come up with different regimes of gas accretion. So if the core masses are smaller than about 10 Earth masses, then the accretion is limited by cooling at all times. If instead you are between 10 to 40 Earth masses, then you start the runaway, but you can never prolong it. It gets halted by the disk accretion during this rapid dispersal. Now, if you're larger than that, and say 40 to 80 Earth masses to begin with, then again, you start the runaway, but now you get halted by the local hydrodynamic flows with the gap opening. And if you're even larger than that, say you happen to be larger than 80 Earth masses, then now the gas mass is going to be completely set by the overall global disk accretion. So what does this all mean when it comes to what kind of planets do you end up with? So here's an ensemble of those planets. And where does this ensemble come from? Going back to this plot, what this plot has assumed is that all these cores sort of started to appear. It was born right at the beginning of the disk evolution. But that doesn't have to be the case. Cores can appear much later in the disk evolution. And that's where this large variety comes in. The different colors here correspond to the different accretion times, where 0 just means the cores appeared so late that it just didn't have enough time, or any time at all, to accrete any gas. 12.1 million years corresponds to the cores forming really early so that it had a full disk lifetime to build their envelopes. So just a reminder of like what this there's some sort of envelope here, upper envelope, and that envelope corresponds to what is the maximum envelope mass these cores can have. And these are sort of summary of what I just talked about in the previous plot, where this part here from about 1 to less than 10 Earth masses, you are always limited by the cooling. And if you go above 10 to about 40, the runaway, you start the runaway, but it gets halted by the disk accretion. And there's another envelope here that sort of has a turnoff, and that's due to the local hydrodynamic flows with the gap opening. There's a turnoff here where as you increase in core mass, the envelope mass fraction drops. And that's because the more high mass cores tend to carve out deeper gaps. So you just kind of deplete the local gas reservoir. There's a very sharp cutoff here in between about 0.1 to 0.4 Earth masses, and that corresponds to this isothermal maximally cooled envelope, the absolute maximum mass that any given core can have. Right. So just looking at this plot, I've also broken them down into different categories. We started this discussion by looking at why is it that when we look at the planet occurrence rate, there seems to be this clear divide right at around the Neptune-sized planets, which corresponds to envelope mass fraction of about 10%. So this is the divide that we have, where for any planet with the envelope mass fraction larger than 10%, then they have to come from the more massive cores. So that's all in orange, and if you look at the median of that, then it's about 10 Earth masses. Whereas for the smaller, more gas-poor planets, it can come from a larger variety of the core masses, but they are peaked more around the smaller cores. So where does this divide come from? So it basically have to come from about 10 Earth masses and larger, which means these large planets, the sub-Saturns and the gas giants, they must start from massive enough cores that they trigger the runaway, but they never prolong the runaway, so that those sub-Saturns that we see are basically the failed gas giants. Another cool thing from this plot is that if you look at sort of the diversity of the envelope mass fraction that we see here, which again, if you try to look at this and convert them to the observables, these also correspond to the radii of the planets. These massive cores, depending on when exactly the cores form, can be either gas-rich or gas-poor. But if you look at the small planets, they can only be gas-poor within a finite disk lifetime. So what this means is that if you go to perhaps more metal-rich stars, which likely host more metal-rich and solid heavy disks, which have the potential to create more massive cores, they're going to have a larger possibilities of harboring a larger diversity of planets. And in fact, we do see this in the observations, where if you look at metal-rich stars versus the metal-poor stars, the metal-rich stars tend to have a wider variety of the different sizes of the planets compared to the metal-poor stars. So this may be the reason why. Now, in this plot, I've actually just kind of linearly sampled the accretion time, but I didn't say anything about what exactly sets the distribution of the accretion time. And that all depends on how exactly the cores have assembled. So how do cores assemble? When we consider the core assembly and planet formation, they form in a disk of gas and dust. So we have to consider them in the context of the disk evolution. The disk gas dissipates over a million-year time scale, so that at early times, the protoplanetary disks are both gas-rich and solid-rich. And as time goes on, the gas that's in the outskirts, outside about 1 to 2 AU, they get blown away by photoevaporation. Those that are on the inside get strained onto the host star, so that at late times, the disk becomes gas-poor and solid-rich until you wait for about a few million years and longer, then you end up with the planetary systems that we currently see, for example, by Kepler and also RV surveys. So if the cores form really early, there's lots of time to build gas. You also have to worry about the planet-disk interaction, so maybe there's some sort of migration. If the cores form late, then there's not enough time to build their gas, so they're going to become gas-poor planets. And maybe when they form, they're also going to barely undergo any sort of migration because there's not much gas in the disk to push them around. And if the cores form so late that there's no gas around at all, then perhaps this is how you can create a completely bare rocky objects. In the exoplanetary census, most of the planets actually lie in this regime where you have gas-poor objects with envelope mass fraction of just about a few percent, like the super Earths. So right now I'll focus on the formation, sort of late time formation in this gas-poor era. Now in the gas-poor era, there are, just like gas accretion, there are multiple modes of core assembly as well. For those of you who are not in the exoplanets, you can actually divide them up into like major merger versus minor mergers. So major mergers is something like giant impacts, for those of you who do think about planet formation. And minor mergers is like pebble accretion and planetesimal accretion. But those major mergers, these giant impacts, they're much more likely to occur in the late stages when there's not much gas around. And that's because in the gas-rich era, gas can damp away the eccentricities really quickly. So it's going to be very hard to cause any collisional mergers. You need to get rid of the gas so that the gravitational stirring between these smaller protocores can pump each other's eccentricities and allow the collisional mergers. So based on this, just like those of you who work in like extragalactic astronomy, you can, in planets, you can also sort of draw out like a core merger tree, just like galactic halo merger trees. So one can think of this again in the context of the disk evolution. In the early stages, there's lots of gas compared to the solids. There's going to be a lot of migration and the eccentricity damping. So you end up with just smaller protocores. And over time, as the disk gas dissipates away, they can merge and merge and merge, and finally becoming the final planetary-sized objects. And this is the actual in-body calculations done by Becky Dawson. And wherever these lines cross is where you have these collisional mergers between the pairs, or sometimes the triples of those planets. All right, so then one can ask the question, how depleted should the disk gas be to allow this cores to merge? One can approximate that by balancing the merger timescale or orbital instability timescale to the eccentricity damping timescale. And merger timescale is a very sensitive function of how spaced apart these planets are. The present day Kepler planets, their spacing is about 14 mutual Here radii. It's sort of at the edge of the stability. And that means within an error bar, the previous spacing just before the last doubling is anywhere between 7 and 11, again within the error bar. So for those kind of spacings, that corresponds to envelope. That corresponds to the disk depletion of about 4 to about 7 orders of magnitude with respect to the minimum mass, sort of like solar value. Or that also means solid to gas ratio of about 100 all the way up to like 10,000. And what's interesting is for this mergers to occur, this kind of solid to gas ratio that's required for this merging of the final cores, they also correspond to the solid to gas ratio, or rather the gas depletion factor, so that when these cores emerge, there's barely going to be any migration. In other words, the type 1 migration timescale is going to be longer than a few million years. So that's actually fortuitous, because this tells us that these planets, when they form and accrete gas about this few percent by mass envelope, they're barely going to move. They're just kind of going to stay there. So this is the picture of sort of in situ assembly. And why is that fortuitous? Well, as I will show, that also gives a natural explanation as to why we have this particular morphology in the orbital period distribution of these small planets. So here I'm just focusing on the small planets, less than the Neptune size, less than 4 radii. And as I mentioned before, they tend to go up in number up to about 10 days, and they plateau off as you go to longer orbital period. And what's remarkable is that this particular shape is consistent between different stellar spectral types. And this kind of curves has been shown like way back by Andrew back in 2011, and also again by people here, Heinz Mulders with Ilaria, who's shown that this remarkable consistency between the different host star spectral types. So then, how do we explain this slope, and why is there this break? Why does it plateau over here, and why is it so consistent between different stellar spectral types? So I'll start by giving you an answer. So the answer for this continuous rise, or rather a continuous fall as you go to a shorter orbital period, is that disks have holes, and you cannot really assemble any planets inside the holes of protoplanetary disks. So how do we get a sense of the distribution of the sizes of the protoplanetary disk holes? We cannot resolve them. We don't have any technical capabilities to resolve those inner holes of the protoplanetary disks. But what we can use is to use the rotation periods of the Premain sequence stars. And that's based on the physics of magnetospheric truncation. So heuristically, for the Premain sequence stars, they are highly magnetic. Their magnetic field lines are going to thread through the disk, and that's going to impart some magnetic pressure, magnetic stress force, so pressure force that pushes the material away from the star. But we know this is an accretion disk. We can detect the accretion rate onto the star. So there's a ram pressure that's pushing the material towards the star. And where those two forces balance is where we first expect the truncation to occur. And in this geometry, there's an angular momentum transfer between the spin of the star and the orbital motion of the gas. So that at equilibrium, we would expect the truncation hole of these disks to coincide at the co-rotation radius with respect to the spin of the star. And I have to admit there's a lot of assumptions and uncertainties that go into this. It's a very messy subject. There's a lot of different physics that goes in there. However, I'm still enthused by the observational evidence of truncation near the co-rotation given by the Dipper stars. And these are young stars that are characterized by multiple periodic signatures. For example, this is one example from a young star, NGC 2264. You see two different components. There's a star spot, which has periodicity of about 3 days. There's another much deeper dips that also has a periodicity of about 3 days. So at least for this particular object, the idea is that there's some dust grains that got entrained by the gas flows that got lifted up by the stellar magnetosphere, and it's just co-rotating with respect to the star. So if you go out there and collate all the known and measured rotation periods of Premain sequence stars, so Tauri stars, then this is how it looks like for one particular cluster. It peaks at around 10 days and falls off as you go to shorter and shorter rotation periods. Just like the planet occurrence rate, which breaks at around 10 days and falls off as you go to shorter and shorter orbital periods. So maybe this fall off here is simply probing the planets that were assembled at these inner edges of the protoplanetary disks. So let's test that idea. So we're going to make an ensemble of planetary systems using two different classes of model, because how we distribute the planets depends on how we think they have assembled, or how we think they have part to where we currently see them. So the in situ scenario is very simple. You just randomly distribute the planets in log orbital period. We draw the inner edge from the empirical measurements of the stellar rotation periods of young Tauri stars. And out to 400 days, we just randomly distribute planets in log orbital period. Why log? Because dynamical stability tells us that these planets need to be spaced apart by some units of mutual here radii. And what about migration? The classical expectation of migration is that as soon as the innermost planet parks at the inner edge, the consecutive following planets should park at the mean motion resonances. But there are some lot of more modern calculations that tells us that maybe that might not happen, especially in multiplanetary systems. They might be susceptible to orbital instability. So in that case, we'll just say that all the planets, as soon as they get to the inner edge, they're just going to merge. So 3 different distributions, largely 2 different classes of model. Let's see which one fits the data the best. So on the left, it's showing the in situ scenario, comparing the theory curve, which is in solid line, just like the data, which are in circles. They plateau down to about 10 days and falls off as you go to shorter and shorter orbital periods. Now, migration scenario, you don't really have a plateau. In fact, if you just increase this further out, then they'll just continue to drop. And furthermore, you have a pileup of planets, which you don't see in the data. And this pileup has been expected for a very long time, like back in the day, Ida and Lim, population synthesis models have also expected this kind of huge pileup of planets if we assume typical migration scenario. And that's because that's what migration does. You just take the planet far out and just transport them back in on the inside. So we prefer this in situ scenario, but even in this preferred model, we have an issue of not creating the same occurrence rate of the ultra short period planets. So what are we missing? Well, these planets are so close in to the host star that now we have to worry about these planets raising tides on the host star. So that these planets are going to undergo a continuous orbital decay. So the idea here is that as the stars evolve off the Premain sequence onto the main sequence, it's going to spin down, so that the planet is going to be it's going to start with sort of an asynchronous orbit, and it's going to lose its angular momentum to the star, but the star is so massive that it basically just soaks up all the angular momentum. It's like an angular momentum bath, so that this planet is just going to continue to spiral in without ever reaching a synchronous state. So, so within that picture, let's see if we are catching this ultra short period planets en route to the host star. And in fact, that's what we find. So within a plausible range of the tidal Q parameter of the star, remember that this is tide spring raised on the star, not on the planet, then we can create this ultra short period planets to about the observed value. Now, in the case of migration, we also can reproduce this observed rate of ultra short period planets, but again, we have this high level planets that we just don't see in the data. So we still prefer this in situ model to create the overall distribution of the orbital periods of these small planets. Now, there are other evidence of tidal decay. When we look at a pair of planets and measure their orbital separation, it widens as you go to shorter and shorter orbital periods, and right at about 2 days. And this is naturally expected by tides, so all these blue curves are the expectations from the tidal model. And that's just because tides is a very strong function of the distance between the star and the planet. So if you have a star and you just have 2 planets, this planet is going to undergo much faster tidal orbital decay than this planet. So that naturally gives rise to this divergence of the orbits. And this is a bit tentative, but when you look at the spin period of the present day stars, you can back out their age by using gyrochronology. And what you'll find is that there's a lack of ultra short period planets around the young stars. Or in other words, lack of ultra short period planets around present day rapid rotators. And that could be a signature of the tidal effect as well. But again, this is a bit tentative and it's a work in progress. We can make some prediction of planets around A stars. The prediction being that if we look at the Herbig A stars, they have very different rotation period distributions compared to Tauri stars. So this is how Tauri stars look like. Herbig A's are much faster rotators, probably because they're more radiative rather than being convective. So what that means is their co-rotation radius is going to be much closer in towards the star, so that by following the same argument as before, we should be able to find planets much closer to the stars, to the A stars, compared to those around the FGK and M stars. So it'll be great if we can actually test this, but it might be hard because A stars are so bright that if you want to get the right signal to noise ratio, you are only limited to planets that are about the size of the Neptune and larger right now. Okay, another interesting thing about the ultra short period planets is that they seem to harbor some signatures of the dynamical upheaval. So this is a relatively recent result of the mutual inclination of multiplanetary systems as a function of the innermost planet's basically orbital period. And you see that there's some signature of it increasing as you go further in. And what's also interesting is that there seems to be some correlation between the inner super-Earths harboring the giant planets, the long period gas giant companions. So about 40% of stars having this inner super-Earths have long period gas giant companions. If you compare that to the field sample, it drops to about 10%. So just randomly, only about 10% of stars have long period gas giants. So we seem to have some excess of this gas giants if it already has some inner planetary systems. So maybe this ultra short period planets could have undergone some dynamical upheaval by the perturbation from these outer gas giant companions. Going back back to the morphology of the orbital period distribution of this small planet. This is the best fit model in solid line versus the observations, which are in circles. How do we explain this plateau down to about 10 days? Those can be explained by planets that have assembled in situ far from the disk edge. And this fall off here can be explained by, again, the in situ assembly near the disk edge. And the ultra short period planets are those that are currently undergoing some sort of tidal and spiral. And this in situ assembly is actually consistent with the gas poor nature of this small super Earth, because they only need about a few percent biomass atmosphere, and that is actually consistent with sort of late time assembly and therefore late time formation. Now zooming out and let's try to connect. Let's just zoom out again and compare that orbital period distribution from between the gas poor objects to the gas rich objects. So again, the gas rich objects look very different compared to the small planets. They just continue to go up, and perhaps that means they have undergone some different formation scenarios. Maybe they formed early as compared to the small planets, which likely formed late. So in this early formation scenario, you cannot ignore the interaction between the planet and the disk. Maybe they have undergone some large-scale migration. And I kind of alluded this before, but with the migration, you are going to have more planets farther out, just because the migration time scale is longer the farther out you go. So planets spend more time out there than on the inside. Can actually write that down analytically. It's pretty simple. Basically, the occurrence rate scales with the migration time scale. However, just like before, we have this pileup again, which we don't see in the data. However, we are talking about, in this case, the subsaturns, which means these are very distended large planets, but with not enough mass that they can hold on to their envelope against the photoevaporation from the host star. So perhaps you can get this down by the photoevaporative mass loss, but and we'll see if that pans out. This, again, is still a work in progress. How much time do I have?
10 minutes.
Okay, sure. And there are actual objects where we can try to look at it as a hint of migration. Caitlin sort of alluded this at the very beginning of the talk. If you just look at this plot of radius versus mass, in general, we follow this overall increase of the radius as a function of mass, but there are some outliers here, and these are what's called as super puffs. So their definition is that they are larger than Neptune, but their masses are really small, down to about 2 Earth masses. And they're very difficult to form in situ. Basically, if you try to form them where we currently see, they're always going to become super Earths, so smaller than Neptune. You have to go all the way up to this blue bar to create the super puffs. And the only way to do it is to first get rid of the dust, and then go to large distances, out to about 2 AU. Then even this tiny 2 Earth mass core can accrete about 30% by mass envelope and become the super puffs. So how do we understand that? Why is it that we first need to get rid of the dust, and why is it that the long distance is more favored? So if you get rid of the dust, then the dominant source of opacity is now the gaseous molecules. And as it gets colder, farther out you go, the rho vibrational modes will freeze out, which means the envelope is going to become less opaque, so there's going to be faster cooling. And I have some demo to show that basic idea, and this is a demo that's brought to you by a theorist. So basically, what we're going to see is this is a hot tea, and this I just poured down the cream, which is going to be tracer of the convective motion, and we're going to see what happens to this convective motion as we cool off this boundary layer using ice cubes. And here I'm just waiting until basically this is the gravity mode to sort of settle down. And I'm placing a metallic lid on top so that I can increase the rate of conduction. So one thing to note: this is not radiated convective boundary; it's a convective conductive boundary. And I just placed the ice cubes here, and we're gonna see a rise of this cream, just because I cooled off the lid. And in fact, it becomes so vigorous that I almost completely stirred up from the bottom to the top. And that's only, I didn't do anything else other than just placing ice cubes on top. So the only thing that changed was just the cooling of this outer boundary. And just that temperature difference alone can regenerate the convective motion of this cream tea fluid. All right. Okay, so basically the superpuffs, they have to form outside, and we currently see them much closer in than 2AU, so they have to undergo some sort of migration. And again, the classical expectation is that we might expect them to be found near resonance. And in fact, that actually is the case. So for Kepler-223, for example, this 4-planet system is confirmed to be in resonance. And for others, it's not exactly clear, but they're definitely very much near this mean motion resonance, compared to the typical Kepler systems, which are nowhere near resonance. And I've just shown you that for those cases, the in situ assembly is the more favored scenario. So going back to this plot, just to summarize, we started by comparing why is it that there's this huge, so clear divide between the morphology of the occurrence rates of the small planets versus the large planets. And I've argued that for the small planets that they have likely assembled in situ, which can explain this overall, the plateau in the outskirts and the fall off here due to the distribution of the disk edges. And it's not shown in this plot, but there are definitely planets inside of about a day orbital period, and those can be explained by the tidal decay. By contrast, these large planets, they may have undergone migration instead of more of in situ assembly. Now, there are some remaining questions here, again, in the theme of how to explain this variety of the exoplanets that we currently see. Didn't really touch on it, but there definitely is a difference in the planet occurrence rate as a function of the stellar spectral type. And I know Ilaria and her group has some theories to this, but I would be really interested in understanding in more detail how that comes about. And you'll notice that this gets cut off right at 300 days because this is all Kepler. We have no measurements outside due to transit, and we're not going to have it. We have to wait for microlensing, so W first, or direct imaging, but we'll probably have to wait for the sort of extremely large telescopes, so 30-meter class size telescopes, to get it down to sort of like a terrestrial Earth size or even like smaller than Neptune sized planets. But it'll be awesome if you can get it, because right now, if you plot mass versus orbital period, it's a complete blank once you go outside 1AU. And also, when it comes to planet formation, it all depends on it's rather sensitive to the initial conditions. So we have to worry about the distribution of the solids in protoplanetary disks. So I think there needs to be some more work done in trying to have more conversations between those radio astronomers, getting this amazing pictures from the ALMA, and getting a sense of the structures of the protoplanetary disks and how it relates to the Kepler sort of like the final stages of the planet evolution, like how it connects to the planet demographics from transit and RV measurements. Thank you.
For a great talk. We've got time for some questions. Jordan?
Yeah, so I was interested in your argument for the in situ formation of the super Earths.
Mm-hmm.
You sort of require the gas to sort of dissipate so that the major mergers can get you those large cores. And that is a good way to slow down the major mergers. But obviously the gas being there is going to accelerate sort of the pebble accretion.
Sure. Yep.
And so can you help kind of explain why the sort of minor mergers don't work for creating larger cores at early times?
Sure. So again, we're interested in sort of the inner regions. And if you focus on the inner regions, the pebble accretion is actually a self-limiting mechanisms. There's this, people will throw words around like pebble isolation mass. So all it means is that once you grow more and more massive cores, it's going to perturb the disk so that it's going to carve out some sort of gap. And the edges of the gap acts as a pressure trap. So it traps the dust and pebbles, which means you starve the core from more inflowing pebbles. So you can actually calculate what is the maximum mass. And unfortunately, it does depend, for example, on the viscosity or the alpha parameter of the disk. But if you like the argument that a lot of the protoplanetary disks may be not so viscous, so let's say viscous alpha parameter of less than 10 to negative 3, 10 to negative 4, then if you calculate what is that pebble isolation mass in this inner regions, it's about an Earth mass or smaller.
For your tidal decay model, does this give a prediction on the mass versus distance of the planets? Because I would expect from the tidal migration that the most massive planets tend to migrate faster.
Right. Excuse me. Right, so are you asking about sort of this?
Well, or more on what's inside the inner edge of the disk, or what's supposed to be the inner edge of the disk. Yeah. So yeah. Okay. Yeah.
Right. So if we're talking about sort of, so to answer the second question, so I actually just stopped the migration right at the edge, but you're right that you can actually go inside and stop at 2-to-1 resonance with respect to the edge. But to answer the question of like what do you expect for the mass versus orbital period, so you're right that if it was just like a single planet per each star, and then you will find that more massive planets on the inside than on the outside. But planetary systems may not be just single planet. A lot of them it's multiplanetary systems. So that actually complicates the picture a bit.
Caitlin?
So you allude to this a little bit with your third point, but can you say a few words about how we might reconcile the in situ model, which I think prefers late time formation, with the ALMA disks, which suggests that at least something related to planet formation seems to be happening pretty early. And I don't know if Joan is here, but there's also these issues of mass and how much mass you have, and so maybe I don't know if Joan wants to comment on whether or not she thinks things have to start early. It just seems like those things might be discrepant.
Yeah, that's a good question, and I always like to say that this is all very inner systems. I'm not saying anything about what happens on the outside. I think that's where we really need this connection between those ALMA images and this. Well, we don't really have it, but you know, what we currently have. And for the inner regions, we just don't resolve it, right? And we have no idea what's going on with the solids on the inside.
Well, Caitlin suggested Jonas next.
I think the form's early, but so looking at your in situ scenario, is there a prediction like if it forms in situ inside the snow line, planets would be dry, and if they form outside and migrate in, they would be wet? So do you predict that they would be dry?
Yeah. Yes.
So someday if we could figure out whether they have oceans, then could we distinguish between an in situ and a migration scenario?
Great question. So I'll first start the answer by saying that I'm actually encouraged by the radius gap that people see, by the photoevaporator gap or Fulton gap, whichever you prefer to call it. And you can actually get a sense of what is the bulk density of those objects that lie, left of the gap, so the bare rocky objects. And you kind of need sort of like rocky material. It doesn't fit like if you assume like ice-coated objects. So that suggests to me that at least the final assembly likely occur this like in situ in the gas, more like ice pore environments. As for sort of like the ocean, that's interesting, and I guess like you will have to think more about whether you can have sort of like the late time like delivery of the ice that people talk about on Earth, right? Like the
Yeah, but
like
that's
cometary.
a small linear.
I know,
if
yeah.
If it was an ice ball that migrated in, you'd have like a very deep ocean.
Right, sure, I agree. So in that case, like you can say something about like if you can detect any sort of like water or like ocean at all, and try to get a sense of what is the bulk contents or sort of like abundance of that. And I think just having one object will not help you. You will have a multitude of objects and try to map it out like as a function of distance or as a function of stellar spectral type or whatever, and then get a sense of like what is the relative and like do you really see these inner planets having sort of deficit of those water material compared to the planets on the outside.
So if I can ask a question too. So in the first half of your talk, you gave this interesting dichotomy to where that you can think of the accretion of gas by low mass planets as being this very hydrostatic picture, and then later it becomes more hydrodynamic or disk accretion. But I guess, as I'm sure you know, like people you know well, like Christopher Mel and Jeff Fung, have shown that even these low mass planets have very interesting hydrodynamic flows that go inside the Bondi radius, and it seems like it could affect all of these cooling issues that we've worked on. So I'm wondering what you think about that and how much those type of flows that people have been studying could change some of these answers.
Yeah, and the degree to which those flows can penetrate inside the Hill radius or Bondi radius, for them it's actually Bondi radius that's more important. Depends on how they treat the energy equations. So if they assume the completely isothermal, then it's just really hard to resolve the inner regions. And what they find is that they can penetrate all the way in, and they don't find any bound trajectories. However, for the simulations that are very careful in taking into account this like radiative processes, then they actually find the bound trajectory within like about a third of the Hill radius. So when I did like all the calculations that I showed here, I actually made a correction so that the bound gas that's relevant for the cooling only goes out to about a third of the Hill radius. Yeah, but you're right. So there's actually a advective layer, and then at around about a third of the Hill radius, that's when you start having the radiative and the convective zone. So that actually decreases the cooling rate by about a factor of 3.
Great. Interesting. All right. Well, maybe one last question from Roshan.
Distribution of the gas mass and the core mass fraction, and also core mass fraction to Earth mass. What's the internal assumption of this lifetime that you're using in the calculation?
Right. So the disk lifetime there, in terms of what actually went into the model, the global sort of the slow depletion time scale, that is set at about 0.7 million years. That's actually convergent with the assumed initial disk accretion time, so that it fits the X-ray data in the actual measurements of the protoplanetary disks. So you might have noticed that the initial disk accretion rate is about like 10 to negative 8 solar mass per year, which is like typical Tauri case. And where I cut off the accretion is when the density depletion during this rapid depletion hits about 8 orders of magnitude, because once you hit that low, the cooling time scale just kind of goes to infinity. It's just so long that you might as well call it the cutoff of accretion. And that's why when I showed that color bar, it went up to about 12.1 million years.
Okay. Thank you.
All right.
There's a pair of sunglasses on the floor here if you've lost your sunglasses on your way out.
All right. And with that, let's thank you.